Hello. Hello, and welcome to this second session on models and learning at RecSys this year. I'm Ben Fredrickson. I'm going to be your session chair today. We have a bunch of really cool presentations coming for you, and the first one is going to be Dilina Rajapakse talking about fast and accurate user cold start learning using Monte Carlo Tree Search. Come on up.
All right. Thank you for the introduction. Hi, everyone. My name is Dilina Rajapakse, and I'm a PhD student at Trinity College, Dublin. So I'll be presenting our joint work with my Professor Douglas Leith on fast and accurate user call start using Monte Carlo Tree Search. All right. So I think everyone is familiar with the typical user call start problem. That is when a new user arrives to and starts using the system, and the system has little to no information about the user. So typically this is handled by one of the most common approaches are using active learning, where the recommender tries to recommend items to a user and get from the feedback of the user, it learns the preferences or the interests of a user to provide better and more personalized recommendations. So how we handle this problem is by using a cluster-based recommender. So when we have the information from existing users, the main information we use are the item rating informations. So we use this to cluster the existing users into different groups, typically based on their preferences. And then when a new user arrives, we try to estimate which group this new user belongs to. So our goal is to accurately estimate what group this new user belongs to, and we are trying to do this with fewer items as possible. And at the end, we are also hoping to have a computationally efficient algorithm which can be used in a practical recommender system. So this is like the overview of our recommender. So when a new user arrives, we are recommending an item, and we are getting the explicit feedback from the user to update the group memberships, which is the probability of a user belonging to a particular group. And we do this for a certain number of iterations, and we try to estimate the user's group. So one thing to note is we are only using the user item ratings. We do not use any content information or the demographics of the users of items. And we rely on the existing user data and the cluster information. So our recommender is based on Monte Carlo Tree Search. The Monte Carlo Tree Search is a reinforcement learning algorithm which is heavily used in gaming applications. So what it does is it performs a series of simulations to find sort of like the best move to do. So in our approach, we adapt this to recommender systems, where each node or a state represents a possible item to be recommended to the user. So we do a series of simulations using the training data, or we use synthetic data in this case, to find the next best item to recommend to this new user. So in the selection stage of the Monte Carlo Tree Search, we are using the famous upper confidence bound approach. So this gives us a balance of exploration and exploitation, where we sufficiently explore or run simulations on all the nodes, and later on we are focusing on the promising nodes by the exploitation. So group memberships, when we have clustered the existing users into different groups, we are able to model these user ratings of a particular item as a Gaussian distribution. So using this, if we have one item or one rating or a sequence of ratings, we are able to determine the probability of a user belonging to a particular group. So using these group memberships, we move on to the rollout policy, where this rollout policy defines how we do the simulations and how we calculate the rewards. So once the tree reaches a leaf node, we have a set of items selected from the tree. And if the user has rated any items beforehand, we have a series of items, V1, V2, likewise, where we have the actual rating from the user. So for the items which we selected from the tree, we are using synthetic ratings belonging to a particular group. And for this entire sequence, we are applying the group memberships and trying to determine what reward to provide to this simulation, to this node. So as you can see, as more number of items are recommended, the graph shows the actual group membership or the likelihood of the user. So we can see that the distribution converges to the actual group of the user. So if we adopt this and we use this in our rollout policy, where we sample the ratings based on this distribution. So as more and more items are recommended, we can make sure that our Monte Carlo Tree Search is using training the synthetic ratings from more synthetic ratings from the actual group which this user might belong to. And one of the limitations in Monte Carlo Tree Search is computation and memory, because usually we need to do a large number of simulations to find an optimal solution. So here we define an heuristic where we determine the number of simulations to be done in terms of the number of groups and the number of items. And also, as previously I said, that as we go on, we get more training data or synthetic ratings from the actual group of the user. That means we can reduce the number of simulations done in the preceding iterations. So in this case, we determine the number of simulations using this, and we can see that as more items are recommended, we need less and less number of simulations, which means our algorithm gets faster and faster as more items are recommended. And when we take a recommended data set, as if you can see the Netflix data set, it has 17,000 items, over 17,000 items. And if we use this in a Monte Carlo Tree Search, we will be limited by memory. And if we are not, we will be still limited by the computation to find a proper solution. So we use the idea of best distinguisher items, where we try to find items which can differentiate between two groups. So by using this on different pairs of groups, we are minimizing the number of items used in our experiment, such a way that we can efficiently use the Monte Carlo tree, like overcoming any memory limitations or computation limitations. And we have done some minor improvements where we noticed some accuracy improvements as well as performance like computation improvements, where we rather use the most visited node than the highest reward, because we noticed that the upper confidence bounds exploitation process favors the node which has the highest average reward. And also the random rollouts, which are typically used in Monte Carlo Tree Search, gave slightly poor results in our approach, because we noticed that looking ahead for more items will actually give less performance. So this is our experiment setup. So we did not stick to one specific domain. We used 3 domains, Netflix, Goodreads, and Jester datasets. And for the baseline algorithm, we use the decision tree, and also we are comparing against the cluster-based bandit, which has shown superior results. And the metric we are using is the accuracy, which is how accurately we estimate the group of the new user. Okay. So here we can see the results we achieved for the Netflix dataset. And the plots also shows how the accuracy changes with the more number of items recommended. So the experiments were done for 4, 8, and 16, 8, 16, and 32 user groups. And for each group, we can see that our Monte Carlo Tree Search is showing better results compared to the decision tree and the cluster-based bandits. And this can be seen across all the 3 datasets, the Jester dataset, as well as the Goodreads dataset. And if we dive into the group-wise accuracy, that means the accuracy of estimating for each group, we can see that we consistently show better results throughout all the groups compared to the decision tree and the cluster-based bandit. And apart from the accuracy, we also focused on the computation and how viable this algorithm is when implementing in a practical recommender system. So as you can see that we have achieved near real-time performance using our Monte Carlo Tree Search. And one thing to notice, this is a sequential algorithm, so we are only using a single core for these benchmarks. So if you need to provide cater multiple users at the same time, it's possible to use multiple cores and do the recommendations parallelly. So in this paper, we have proposed Monte Carlo Tree Search as a good way of solving the user call start problem. And we also, other than the accuracy, we have focused on the implementability of this and how scalable, how to implement this in a scalable system. Yeah.
Thank you. So we have a couple of questions on Slido. I guess the most upvoted one right now is, how are you generating the synthetic data? Is it possible that your approach works well with this synthetic data, but might not generalize well to real-world data sets?
Yeah, so when we have the user item ratings from the data sets, we use a matrix factorization-based clustering algorithm to group them into different groups. And once we have those clusters, we sort of like model the item distributions, ratings into a distribution. So that's how the clustering is done.
Excellent, thank you. So the next question is, how does your strategy compare with other cold start strategies based on popularity and content metadata?
Yeah, so using the content information and the contextual information is one of the works which can be done in the future, like it is one of the future improvements. And what was the other question? Other part of the question? What was the other part of the question?
So it was using both like other approaches that use like content metadata for cold start as well as popularity features.
Yeah, so in our approach, we noticed that we overcome the popularity bias because always recommending the best item, usually throughout all the groups, we would get a higher rating. So in that case, we will not be able to distinguish which group the user belongs to. So in our approach, the popularity bias is sort of been overcome, and the content information is, of course, in the future improvements.
Cool, thank you. And the final question is, how do you generate existing user cluster? How do you generate an existing user cluster to which the new user is assigned?
We do not focus on like updating the clusters or creating new user clusters yet. So I think it could be considered in future work.
Excellent. Well, thanks for the presentation. Let's thank the speaker.
Right. Thank you.
Yeah.